So we're going to start with Pedro from QuEra, who has done a lot of beautiful work on application development and working with us for the last couple of years.
Yeah, so after 3 days of pestering you with questions, it's only fair that I come last, right? Time for revenge. Yeah, we got this. So we're gonna try to, probably, everybody's pretty tired. We're gonna try to keep this pretty light and maybe do something a little, is ludic a word in English? Like gaming? Like try to get involved. Playful. Thank you very much. Keep it playful, keep it light, so that we relax a little bit and go home feeling like we finished strong learning something. So the title of this is Get Basic Quantum Computing with Neutral Atoms, Chapter 1. We are not doing Chapter 2 today, don't worry about it. But the whole idea is to really get you a little bit more of a feeling. We sequentially, like several times we saw talks about this topic of neutral atom quantum computing, and everyone was, let's skip the details, we're going to skip how these things work. This time we're going to do the opposite. We're not going to do anything with it. We're just going to try to figure out how these things work a little bit and get a feeling for how it goes and how you can think about, in particular, developing programs that are well adapted to the hardware, right? So we've seen many protocols or strategies to create optimal circuits, but frequently I've seen it written, oh, let's create optimal circuits for an application. Like we want optimal circuits for the hardware. The hardware is the one that suffers. Application, yes, it must work as well. But if this doesn't go on the hardware, then like nothing is gonna work. And then we're gonna get my contribution from my friend here, Jan, who is going to kind of exemplify a little bit of this thinking on a realistic scenario that we worked on together. So we have learning objectives here. So by the end of this session, we're hoping here that you'll be able to describe the baseline functionality of digital neutral atom quantum computers. And you should be able to state the constraints for shuttling operations, so operations that move these atoms around. So how can you move how you are not allowed to move the atoms around? And finally, hopefully you'll be able to write down kind of a phenomenologically inspired hierarchy of errors for the system, so that whenever you're designing a circuit, you know what you should be okay with, what you should not be okay with, or should be less okay with. So by now, I hope we have realized that neutral atoms we don't have like a beautiful golden picture for it, right? So we draw. We have these laser twisters. They're holding atoms here. They are the spherical blue objects. We can pack them quite densely. We are holding them in free space, and because we're holding them in free space, we can move them around, and this allows us to encode things in a very flexible way, and it allows us to think about quantum computing in kind of different or new exciting ways. So this is on the bottom right here for you is a picture of our Gemini machine that is currently under installation in Japan. And if you look deep inside it, you will see a few different elements, and here are a few of them. I think it's always nice to know how this works, because it helps you figure out where the constraints come from. So the joke for me is that in AMO we like TLAs, right? So in atomic molecular optical physics we like 3-letter acronyms. Right? So here we already have 2. I've cut the EM and leave with the CCD. That's another one. So these guys, they're really the main players of this technology. So the AOD is the acousto-optical deflector. And the secret about TLAs, I'll tell you right away, is that if you read them backwards, they make sense. As acousto-optical deflector deflects optics via acoustics, via sound. You just read backwards, it makes total sense. You know what they do, right? So it's going to be something that you're going to pass some sound waves, and then it's going to allow you to diffract light, and in particular, shift the position of the main peak of the diffraction pattern and move this laser around, right? We live in kind of meter-size scale. This has to move in this micrometer-size scale, and this is the element that allows us to do that. The other element here is this SLM, is the spatial light modulator. which modulates light in space, right? So it's a special type of active mirror. It's a liquid crystal that you can use to program, to modulate literally, so to change intensity or phases of light in the kind of the transverse direction, and sometimes even in depth as well. If you have seen these figures of like Eiffel Towers and so on with atoms. So roughly the point is SLM holds like it sets up your circuit, and AUD allows you to do dynamics, right? So the SLM is what's gonna kind of print the circuit in some ways, and the AUD is more part of the actual calculation process. And please stop me. We can just chill. And then the interaction with these atoms is going to happen. It can happen either transversely, sorry, sort of perpendicular to the plane where they are being held, or in plane. So here we are seeing this pair of laser beams that are going to be responsible for excitation. With rubidium, we're going to talk about rubidium in a second. We always want 2 photon excitations. We want 2 lasers. And there are many reasons why you want 2 lasers. One of them is because if you didn't, this is going to be very high energy and you would be in the UV. And the UV is hard to have mirrors for. But there's other reasons, right? If you had just 1 laser pointing to one direction, shining in one direction here, you pick up momentum. So it's nice to actually have these guys coming from opposite directions so that the atoms stay put. So I think it's a feature, not a bug. But then it leads you to do 2 photon transitions, which is a bug, not a feature. Both of them are features and bugs. Right? So again, we play with rubidium. Rubidium, if you don't remember where it lives in the first column of the periodic table. It has an address. There's questions in the chat. I don't know if they're new. No. Continuing. So first column of periodic table means quarks like hydrogen, looks like hydrogen, and has 1 electron in the valence shell like hydrogen. And this guy, we're gonna play with a few different energy levels. So usually we're gonna look at the hyperfine split ground state. So this guy is firmly protected. The electron is very close to the nucleus. It doesn't see anything other than like very intense laser beams, and that we kind of focus very tightly on the atoms. And then we have this third state here. We call a Rydberg state. It's any state with a very high energy. So the atom bloats up, it gets large. When it gets large, the polarizability increases. When the polarizability increases, it can entangle. So you're left with some story that's quite interesting here. Right? It's almost as if you had a Q-trit. It's not really a Q-trit because we are going to operate these energy levels kind of asymmetrically. But the 2 bottom ones, they are sort of like a memory or a short-term memory or not error-corrected memory. They have long coherence time, second long. And they're very stable. So they don't see things unless we want them to be seen. And the Rydberg one is the opposite, right? So it's highly interacting. It's gonna see geometrically who is close to you and who is not. And you get to play with this. So it's very nice because you kind of have a inbuilt process for suppressing crosstalk. And if I don't put the atoms up, I can do whatever I want. These atoms don't see each other. But if I get a few guys and send them up in energy, that's when they start to see interaction, and it's like a switch. So that's how this plays in the most kind of fundamental levels. Ultimately, why the way that we play with these guys is really by leveraging the fact that the atoms in the hyperfine qubits, they are very stable, so that we can move them in free space without destroying coherence, without destroying the quantum states, the superpositions that we prepare on these guys, and the entanglement. And we are able to do things just like you're seeing here from our friends at Harvard. You can do sort of the dream of the EPR paradox, right? Where you can put these atoms close together, you can entangle them, we can move them apart, literally move them physically apart, and then when you measure one, you get information about the other. And if you don't move them apart, you get information about the other. If you move them apart, you also get information about the other. It doesn't matter, right? It's not obvious. Like this requires some smart way to interact with these atoms as we move them, but you can see that entanglement can be preserved as we move things physically apart. So you can see that, for example, one of the things is that if you move too fast, like if you accelerate too much, the quality of that coherence, it's gonna degrade. And it's gonna degrade for multiple reasons, Doppler shifts and other things that happen on the system. So those are the basic elements. Do we have questions? I can stay quiet for as long as I need. That's not true.
Question.
Yeah.
You talked about the 2 photon for the 2 qubit gate.
Mm.
How do you do the 1 photon? Sorry,
The one qubit gate. So that's
photon?
yeah. So this is just the Raman transition. So it's just the hyperfine. It's
Is it
yeah.
intermediate level?
Sorry.
Maybe this is too much detail, but what intermediate state do you use for the Raman transition?
So there's no intermediate gates in there, in intermediate level.
Where do you go through for the Raman transition from 0 to 1?
Oh, so I can show you what are the energy levels that we're going to use. There's a diagram in a second, but roughly they are clock states. So it's the states with m equals 0. So they are not sensitive to variations in electromagnetic field.
A question. So you said that the Rydberg state is basically any high energy state.
Right.
So how sensitive the 2 qubit entanglement gate that you apply is to the specific Rydberg state that it was in?
So if you look at Aquila, the machine that you have heard a lot about this week, people using it, we're using 70S, 70, right? The ground state is a 5 because it's rubidium. And now when we look at Gemini, we are down to 57, something like that, right? So there are trade-offs. The larger is your N, the bigger is your cloud. The farther you can go, the stronger they interact. But if you interact too strongly, you're an antenna, so you pick up errors more easily as well. So sometimes it's advantageous to interact a little less strongly, and there are balances, there are trade-offs over there. So even for the analog machine, we use 70, but some competitors in France they use I think 60. So there's those are some of the trade-offs that are going to get pretty much it's distance, it's interaction strength, and then how sensitive you're going to be to decoherency effects. Yep.
Is there an intuitive reason why the interaction potential goes as the distance to -6?
Yeah, absolutely. So as I said, it's a dipole interaction. So dipole is 1 over R cube, and this is like a second order interaction. And then because it goes from S to S, you needed to go to second order processes.
So
and
similar
then
to Van der Waals potential?
it's a Van der Waals potential. It's exactly Van der Waals potential. Yeah. Cool. We keep moving. So what do we do with this, guys? So when you're doing calculations with this, you definitely want to know who are the native gates in the system. And the native gates are kind of at highest level, you can just say that it's really just arbitrary single qubit rotations and controlled Z rotation. So no, not controlled knots, but it is a simple gate, 1, 1, 1, -1, controlled Z rotations. Except that this guy here, we tend to prefer to decompose that into Z phases and rotations in the XY plane. So if you have, for example, a JHZ state prep, so you might recognize this here, right? So go to 0, 0, 0 plus 1, 1, 1. So that's exactly what this guy is doing. What you we want to do is instead this, right? So you can decompose those Hadamards into square roots of y. And in particular here, what you are seeing also is that we are doing some tricks. We are actually squishing all the Hadamards and everything to the same layer so that we have this local, this global layer. Everybody's getting the same. We love global gates. We love global gates, and you should be able to understand by now why we love global gates, because you have seen with your eyes, right? You have seen with your eyes in this picture. Right? So these guys, they shine over everybody. Right? So unless I separate them in space, they shine over everybody. So this means that I can parallelize things by simply placing them together and letting things go. Of course, that this is for Rydberg, that's for single qubit. The same applies for Raman. And then everything else comes down to reconfigurability, right? So this is another cute video. So that I don't know if you can tell, but it's animation. This is not, okay? So this is actually, every single point here is one atom. So if you never saw an atom, so today you saw an atom. And kind of 3 by 3 pixels to see an atom here. And what I'm gonna show you is how you rearrange these guys in order to generate GHZ state in logarithmic number of moves. So be ready, right? This moves, okay? So yeah, goes first, then second, third, and then it goes, and now they go, and then it goes. And you can count, and you can see, right? So it's very easy to see in the first step, right? So the first with the second, now the second with the first with the third, and the second with the fourth, and so on and so forth. I don't know if you can keep up. Let's go slowly, right? So right, so that's the first one. That's the first C naught over there. Everybody can see the C naught. Everybody can see the C naught. Okay. Then now we want to do 0 with 3 and 1 with 2. You agree? I'll do 0, 0. So 0, 2, 1, and 2. And so on. Like there's no secret here to what's happening. You can see with your eyes and it makes sense, right? And then it keeps going. So it's very nice because you can see that all this chain, this ladder of C naughts, it literally is one beam. It's one zap, boom, done. As long as you can kind of organize your layouts and your moves correctly, you do things in single operation stack. Yeah.
I don't know if you're gonna get to this. If you are, just tell me to shut up. But there's, in the first 2 movements, you have the pairs that are very close to one another split up as they're moving. And then in the next 2 movements that are like the bigger movements, they are coming back apart before they move again. Is
coming back apart before they move?
If you look at the first movement where the first qubit interact with the other one.
Yeah.
And then it goes into the next interaction. You're not actually splitting them up before you go into the next interaction.
They're going in parallel, right? Like they're going whoa, like that.
It's like a fully arbitrary movement.
It's almost an arbitrary movement. We're gonna get there as we go right now. So let's look at what is allowed. Yeah.
One more quick. So in the one slide before, you said instead of the Hadamard, you do a root Y on all of them. Is that happening here?
Well, you can't see it, right? Like because the measurements are literally done by kind of it's not spectroscopy, it's not photosynthesis. It's late, right? It's fluorescence. So think about it. It is spectroscopy. It says fluorescence spectroscopy. So you literally have to look at them. So if you are seeing this has been done in the absence of gates. Right, of course, because otherwise you would be seeing your quantum information there, and that would be annihilating the states, collapsing it all the time. So this is just like an animation of the atoms without the gates.
Yeah. So this might be getting under the weeds, but how many AOD to SLM and vice versa transfers are there in this?
So here you're seeing just one pair of AODs. So the one pair, one for X, one for Y movement, right? But that's for this movement. You see just one set of atoms moving at every kind of a movement moment here. Don't know that I can tell you how many we use in total.
So I mean, like, in this configuration, are they all parked in SLM traps?
So the SLM is holding the square lattice, and the movement is happening with one pair of AODs.
Would you put them back after the atom returns?
Put who back?
The atom back to the SLM?
In this case, no, right? So you can see that it goes and it stays there. So there are situations where, for example, I could be hiding the fact that every point here is not one point, it's a pair of points.
Yeah.
Like where I could be leaving them on the AOD or not leaving them on the SLM or not. So that is an architectural dependent question, and I literally can't tell you right now exactly what are going to be the options. That's being kind of defined. Good. So let's look at what are the shuttling rules, what you can do, what you can't do. first thing that you can do, you can take two guys and move them in parallel. No problem. Okay, so they move in parallel, they move side by side, they go, no questions asked. So that's ching. The next question is, can you cross them? And the answer is no, you cannot cross them.
The beams.
Don't. Yeah. So we're getting there. Yeah, but you can move one and then move the other. Okay, so that it's okay, but it's 2 steps. So I give you yellow marks here for that one. Right. So if you're having a hard time visualizing that, my former intern made many animations from it. So it's very cool. And a question that I bring to you is, why are these constraints? Why can't we do this? Why can we do what we can? Why shouldn't we do what we shouldn't? I think collision is a problem. Collision is usually a problem. So besides blockade, the Rydberg blockade, there's a collisional blockade. So if you bring these guys side by side, they will kick and each other and fly away. So you don't want to cross them. I guess it's probably not too hard to imagine why this guy costs yellow marks instead of green marks. Any opinion on why?
Steps.
2 steps, but what happens in 2 steps?
There's 2 beams.
There is a single beam, but I think that I guess what you're trying to say is that I'm picking and moving and picking and doing things in separate. So which is the case. There's a little bit of a time constraint there, which is not a huge thing for this.
An intermediary state that you may not have planned on.
In this case, yeah. So that costs some time. So to be honest, this is not that bad. But yes, you want to avoid doing kind of picks and drops. You want to do that as much in parallel as you can. So atoms cannot collide. Atoms cannot change order. So if they cannot collide, they cannot change order. You cannot have 0, 1 become 1, 0 in a single move. You have to do that and that. So those are 2 moves.
You move them at different speeds.
You can move them at different speeds, right? Like I just showed this guy, right? So this guy, you see that they are moving at different speeds, right? Like one is going farther than the other.
They can do the same path at different times. Just slower one than the other.
Yeah. So ultimately what we have is a grid. So imagine that these atoms, they live in a grid. That grid can be deformed, squished, but the kind of rows and columns of that grid, they cannot shift. So yeah.
Again, if you have, arbitrary number of lasers, you can do all kinds of stuff, but in a realistic system, I mean, all of the movements that you've been showing so far have been very much one that when there is simultaneous movement, it is following essentially a parallel vector. Is that a hard requirement, or does that just fall out of your examples?
So the requirement is that it's grid movements. So if I had a patch of like 3 by 3 or 10 by 10, whatever it is, I can squish that patch. I can deform that patch, and I can move the whole patch together,
Okay.
but I cannot swap things inside of that patch at once.
So the movement isn't entirely, so there's 2 classes of movement. There's sort of everything's following the same vector, and then there's basically.
And there's some, yeah, exactly. Yeah, cool.
Is there a reason why you cannot do the swap? Like if you would go like one goes above and the other goes below?
Yeah, so just think, if you think of the grid, it's very clear, right? Like you would have kind of rows or columns that they would be swapping. So this is a condition that comes from the fact that the AOD it generates diffraction. So the multiplexing of points, it comes from a diffraction pattern, and now you have like a tensor product of x and y on this. So that tensor product does not allow us to rotate between the x and y ultimately. So to that point, this is an interesting one, right? This is not allowed. This is not allowed because you're kind of degenerating like the grid, right? So even if the atoms are not colliding, they're ending up one on top of each other. And that would mean that the grid that you started with had columns that overlapped. So this ain't no good, and the reverse of that, it ain't no good either. Yeah.
You have to effectively think about every position here filled in as you move, when you're moving the grid. Like you're saying, you can't do this movement because if there was something next to the bottom.
No, I'm not allowed simply because these guys start separate vertically and they end up overlapping vertically. That's why, and horizontally the same would apply. Yeah. Cool.
Wait,
Yeah. 2 minutes? Really?
2 minutes? Okay, then I'm not asking.
Yeah. Do I have 2 minutes?
I need 10 minutes.
He needs 10 minutes. We'll take it easy. We'll take it easy. So there was a question.
So you said many to one is not doable.
And one to many isn't
one to
either.
many-
Yeah, same
But like
story.
you just showed us, like there was a one to many, no? Was it?
Um,
In the example that you showed us, like there were two atoms that are really close to each other that end up going separated.
but
one, yeah.
yeah, but the story here is that this is one movement, this is one movement, right? And they are starting in parallel horizontally, and they're finishing in parallel horizontally.
Okay, so them being close doesn't mean that they're overlapping
Yeah.
vertical. Okay, cool.
Exactly.
So you're sensitive to that.
Exactly.
Okay.
Exactly. Let me keep going here just because. So this is just a little bit of a system overview. This is from a paper that's yet to come on Gemini. So I was mentioning that I had a little diagram on the energy levels that are being used. So this is it. So both of them are n equals 0 states in the hyperfine split. And again, those numbers, they are just the numbers that were used in this magic states distillation paper that we did maybe a year and a half ago or a little bit more. But it gives you a little bit of a feeling for distance and sizes that you can expect to be able to play with. So in just a couple minutes, just want to briefly tell you that these guys can be operated in multiple ways. Like there are multiple kind of zone architectures that you can think about. You can have all the atoms in a single zone, and that single zone has all your beams kind of shining on top of every atom. Or you can kind of separate them in space, and then you have a zone which has this global beam and a zone that does not have this global beam. And so these are two compilations of the same protocol. One in a single zone, so it's both of them are the GHZ, and the other is in the two zones, so you can get a feeling for what happens. You might think that single zone is always going to be more efficient. It's not the case. You might think that two zone is always more efficient. That's also not the case. It really depends on the protocol. It depends on the layout. It depends on kind of everything that you're doing. So that's what I'm saying. That whenever you plan on a circuit. If you really want performance, these guys, they have to look at each other. Your circuit has to look at your hardware, and your circuit has to look at your application, and the hardware must be aware of all of it. I will go more or less quick through this, but the bottom line is we have global gates and we have local gates. So these qubits can be, even for single qubit gates, they can be addressed individually or in their totality. Totality is always better than individually. So whenever we have a gate that is global, we are going to favor that, and usually by even a factor of 10 in error rates. Entangling, so whenever you generate entanglement, if one qubit is alone under that beam, it will suffer. It will know that there was a beam that tries to operate on it, even if it doesn't have a pair. So we call that the unpaired or a spectator atom. And then shuttling, of course, if you try to move, this guy is gonna pay. But you see that, like I was saying, that we had that situation where we had kind of two moves. So the sitters, whenever someone else is moving, there's someone that is sitting. And the people that are sitting, they're gonna pay a little bit for being sitting while the rest is moving. And that boils down to a noise hierarchy, and which is roughly gonna be where we're gonna stop. As Milan was saying, CZ, two qubit gates tend to be the main source of error on most architectures, and that applies to us as well. So two qubit gates cost almost as much as moving. Moving costs a little less. Leaving someone unpaired while a CZ is being applied costs about as much as moving. And from there on, things only get better, right? So sitters and single and local and global beams, single qubit gates, they are pretty performant. And it's interesting to know, I think that something that is very important is that these noises are very biased. So they are Z-biased. So if your protocols have more gates that are in Z or in the XY plane, that will have a consequence to your performance as well. So I will leave you with this picture of what good circuits can look like. You want to see many moments with lots of people that can be operated in parallel. And maybe I'll call Jan to give you a feeling for how to use these lessons in a practical scenario.